Hi, everybody. Thanks for joining today's session. Today's session is about Delta Lake, and it's really a misnomer, other lakehouse formats. I'll not be covering other lakehouse formats, but then this is the general architecture of other lakehouse formats. So once you know this, you'll probably be good to go for, say, Iceberg or Apache Hudi. So that's why I've just written it so that you just correlate with other lakehouse formats. Okay. Let's start. All right. So I'll just start with the problem statement, and we'll see why we moved to this lake house format or Delta Lake in the first place. So we had something, I think this is already known by most of us, DP merge, data partner merge, where we would keep the full snapshot of the data that comes in for third party for each data partner. And this full snapshot is augmented by daily change data or daily AEL as we call it, that augments the full snapshot. And earlier we used to run Spark jobs, which would merge on a daily basis the change data with the full snapshot. Okay, so why we did this? As you can see, firstly, we needed to maintain a RDBMS like stable structure on blob storage, right? So that we could query the data and get, we would run predicates maybe based on mails, Bangalore, right? These kind of queries so that we can facilitate, and that required most updated, data, which very much replicates a RDBMS table. So that is one. Second was we needed transaction processing capability. So we have a concept of versions in our pipeline. So in our profile store as well, you have versions. So whatever query you're running on a previous version will have very different result from what you're running from on the current version, right? So there was a notion, although implicit, but there was a notion of transaction processing. You can think of all the updates that are happening, the CDC or the change data capture, the change data as being the updates on the snapshot. And we would maintain entire snapshots of different days to emulate this transaction processing. And finally, if you see, we needed versioning capability because each day's snapshot merged with the CDC is a version of that particular day. Till that time, we always had a version, so that anytime if we find that we have merged corrupt data and we have merged there's some problem with the data or some maybe the Spark job has failed, we can immediately roll back to the previous data. So all sorts of RCAs and stuff needed to be done. So that's why we wanted to maintain such a structure. Drawbacks, obviously, since you are merging the entire change data with the full snapshot and not tagging them based on inserts, deletes, right? There was no particular change data capture. You always had to take two full snapshots, do a diff between them to find out what is this change data. So that was the major drawback. That's why I've made it bold, because we had no change data capture, and then there was this shuffle. We employed a huge shuffle which would go about doing a group by with a map groups. Now this would again give us a lot of improvements when we are using Delta, and we'll see that that is more towards the profile store side. But overall, we wanted to get rid of this shuffle as well and only merge the change data on a daily basis. So I'll talk about that later. But our shuffle was somewhat, we got relief in partial aggregation. We used map groups with group by, which provided us with partial aggregation. So I'll just move on to Delta Lake. So what was our goal really? So from this problem, if you see, the goal that we were moving towards is we wanted some sort of CRUD operation, right? Upsert, delete, some sort of CRUD operation on our data, which is there on blob storage. Now, that has been a classical problem. I'll talk about it in the next slide. But we wanted some sort of CRUD kind of transaction kind of capability on blob storage. And again, the same, the next 2 points are probably same with Spark as well, that we wanted efficient query processing capabilities. So our data is partitioned in a way, or data is structured in a way so that we can process minimal data and get process bigger queries basically. And this is something already provided as by Spark. Delta did not do much here, but Delta did augment it. And third is with Spark, if you see, or rather with the entire big data revolution, even if we go back to Hadoop and MapReduce kind of processing, this concept was floated where the storage format or the data actually resides outside. There's no specific DB where the data resides, right? There's no RDBMS. Who is managing the file system, right? We've got separate file systems. Earlier we had HDFS, and then we had blob storage like S3 GCS, who is separately managing the storage format. And then we came up, then there was, in old times, there was this MapReduce processing. We had Apache Crunch, Apache Beam, and finally we had Spark. They kind of took the concept of compute, the processing engine, which could actually pick the data from these blob storage and process them in memory. Spark did it in memory. Probably MapReduce did it on disk. But then all these concepts became loosely coupled, which were tightly coupled in an RDBMS, right? You had to write RDBMS queries and then run it on RDBMS. So all these became loosely coupled. So we still wanted that. We never wanted to go into some sort of data store where we would be tied by the dialect and the DSL of that data store and writing some queries on top of it. We still wanted the advantage of Spark, the advantage of decoupling these storage formats and the processing engine. And yes, and finally, the guarantee. There are two important guarantees: atomic reads and writes. Somebody reading the data and somebody writing the data should not corrupt our blob storage. And then somebody reading the data, while they're reading the data should not change, and they should not get inconsistent view of the data. So, and finally, concurrent processing. Obviously, we want to process the data as fast as possible with as many jobs as possible. So we wanted concurrent processing capability. The same file, if we, in current Spark, if you see, the same data, if you want to process, there is no way to do concurrent processing, right? We cannot work with the same data set, and while it is being read, it cannot be written. But all these became our next goal that, we, not just we, Delta is looking to alleviate. So probably I would, I'm assuming a little bit of working knowledge of Spark, not a lot, but just a little bit of how it works, how the MapReduce processing works. I'll not go into all those details, but I'll just assume the prerequisites there. So, okay, so this is where I talk about the transition of how it moved, right, from databases to data lake. Like, why did we move from, say, a MySQL to a data lake kind of architecture? Because we wanted to decouple the business logic from the storage. The storage, we did not want it to be these data stores, these databases. So that was enabled by these data lakes. And finally, we wanted to independently scale compute, independently scale storage, right? In today's world, we know S3 can store any amounts of data, and that has nothing to do with the compute. Your compute wouldn't slow down because of that. At the same time, you can, with Spark or say Beam or Dataflow, you can independently scale compute as well. So we definitely got these kind of gains from data lake, but the cons was the reliability part. What I was saying, that once we are doing, once we try to do concurrent processing or try to work with the same data, read or write on the same data, we actually lost that. But that is what Delta is now attempting to bring into the entire framework. If you see, they're trying to bring the transactional reliability of a database. The kind of transactions that is possible on database is now possible on Delta, and the horizontal scalability of data lakes. By the virtue of using a data lake, you already have that. So moving on. So let's focus now on what is Delta Lake. Okay, so Delta Lake, contrary to a lot of blogs and stuff, it's not a processing engine or anything. It's just a storage format. Okay, Delta, if somebody asks, that's the one thing. It's a file-based open source is there. It's a storage format. That's it. It's a way of maintaining your files in. It's a way of maintaining your files with some additional metadata. When I say files, the out of the box what comes is Parquet, but you can configure it. Theoretically, they don't provide much support on that. But with Parquet, there is some additional metadata. That's it. That is Delta Lake for you. You have your Spark job, which processes your Parquet files, the same old Parquet files with some additional metadata. Together is what they call it the storage format, the Delta Lake storage format. Okay, so all these lakehouse, whenever you hear about lakehouse architecture, you should immediately think about the storage format that we are alluding to. What does it bring? It brings ACID transactions. Obviously, I was already referring to that. It brings CRUD operations. Your use cases probably would be change data capture, like I said, I explained for our use case. Then there is slowly changing dimensions, SCD, where you may be getting your data, and over a period of time, the data is changing, right? And there are different types of SCD. I won't go into that, but the point is that is one of the use cases. If your dimensions are changing slowly, you need if you already see if something is changing slowly, that means a version is tied to it. You want to query those versions and come up with how it is changing, right? So hence the concept of slowly changing dimensions. And finally, streaming upserts, right? You have data which is not coming regularly, which is coming in spurts, and you want to do upserts into your system in a stream, in a real-time manner, right? So all these things are supported by CRUD, and which brings me to the next point. If you see unified stream and batch processing, the best part right now is all our pipelines are stream compatible. So with the upgrade from Spark to Delta Lake, we have actually brought in stream processing into our system. Okay, if today I can play any kind of stream, any kind of batch data on our entire targeting pipeline on both DP merge and MPM, as you famously know it. We can bring both stream and batch processing. So there is not much changes that is required, and we can do it by writing some, I think, 10 lines of code probably. So we have actually, that's a good thing that we have actually upgraded to a stream-based processing as well. So Delta actually does this for us. They provide both stream and batch processing unification. Obviously, it runs on top of your existing data lakes. Otherwise, nobody would have moved. It is compatible with Apache Spark, and a lot of people think that, okay, Delta is only compatible with Spark, but you can use other processing engines with Delta as well. It is configurable, although out of the box, it comes with Spark, but it is configurable so that you can use something like, say, a Trino DB along with it. So you can use other processing engine. You can use a Snowflake along with it, okay? And it's just a marketing strategy that the Spark guys have, that, to boost Spark with Delta, basically. Finally, the most important thing that I think we are leveraging is audit history and time travel. So with the concept of versions, you already have a way to do time travel, and you can go back in time, look at your queries, look at how your data has changed over a period of time. And that also solves, partially your GDPR cases. If you want to maintain audit history, if your client wants that, want to know that whether at a particular time certain data was deleted or not. Earlier, with Spark, we had no way of defining what data was deleted. I have a small demo at the end I'll show. You'll see exactly what was inserted, what was deleted from the system. That is stored as a matter of fact, as an audit history. Okay, and finally, schema enforcement and evolution. This was already there with formats like Avro and stuff. They have obviously augmented it. So it is also there. So I'll quickly move on. So this is the basic usage and operations. I'll not delve more into the operations. Rather, we'll try to look at how these operations work internally. What do we mean when we do these operations? So first is getting Delta into your system is very easy. Your regular Spark shell that you run, you just run it with this package, which I have highlighted. Delta core something. You just import this package, you're good to go with Delta. This is the open source Delta. Databricks has its own Delta Lake, which has a few more functionalities, few more capabilities, which I'll not be covering, but you can check out the documentation. Second is creating a Delta table is very easy. Earlier, your code would look like, if you see in red, it would just look like dataframe.write.format Parquet saved to a location. You just have to change it to Delta. That's it. You're done. Your tables are converted into Delta tables, and you can leverage all the advantages that it has. There are two modes that are supported: append and overwrite. Okay, append is basically when you want to add to a Delta table. It would get added in newer versions, and overwrite is the current version will get overwritten with a certain data. Old data will be removed. When I say remove, take it with a pinch of salt. I'll explain that what it means. Okay, read again is very simple. You read it with the format delta. That's it. Okay, I put a select star from for people who might be using Databricks runtime. So you just have to read with the, like you read with the format Parquet, you would read with the format delta. That's it. Okay, next, I will not be covering Metastore here, but then Spark and Delta already provides a Derby in-memory, Metastore, which works on Derby actually. So once you use this format, it creates an in-memory data store, but there is no particular catalog where the location of your tables and stuff, all these are maintained, right? But when you use a Hive Metastore, you have to just change this command to save as table and give your name. Then the location and everything will be handled by, the Hive Metastore. Basically, that's what I wanted to highlight. Sorry, Satish. So I didn't get the question, Satish. Sorry.
Okay. So you have the mode, right? When you're creating the Delta Lake.
Okay.
Then when the recent version of the file is getting in, and when you're doing the merge, which is the operation. So I'm just asking, suppose you have a conflict resolution strategy there for your merge, and you have a append or override here. Are those connected was the question. Probably you can take it later. If you
yes,
want to cover.
I'll actually be covering that actually.
Yeah. Okay.
Yeah. Okay. So basically, for our work use cases, we are not using a Hive Metastore. If you want to persist your tables, you want to make them a first-class citizen. You just don't want to have them on some say S3 or GCS. You want to make them first-class citizens, and you want to manage their locations centrally so that you can use them directly. You probably want to look at Hive Metastore, but we are not using it much. And what are the other operations that are available? There is update, delete, insert. Obviously, I've spoken about CRUD. Merge is a special upsert operation that I'll be talking about. So these are the operations that are generally available. Okay. So moving on. Okay, I spoke about this in this slide, scalable metadata handling, right? So the fourth point here. So I just wanted to touch upon that. So if you see here, Delta Lake, as I said, what is Delta Lake? It's a storage format which is equal to your Apache Parquet files plus your metadata, right? So this metadata, now I'm talking about the metadata part of it. The metadata is stored along with your data, okay? And this is the structure on the right-hand side. If you see, this is the structure of that metadata, okay? You have a column called add, remove, something is happening here. I'll come to that. But point is, all the metadata of your data, what inserts happened, what files were added, what files were deleted. These kind of operations are stored along with the data. Why? Because when you look at a typical, list operation on your blob storage, that's typically very slow. And that's what Spark and other systems do. They do a list operation on your blob storage, okay? And then when there are corruptions, the blob storage doesn't track your corruptions, right? So if you see a lot of these transactions, lot of these transaction processing, concurrency, they depend on how you manage the metadata, what operations happen, okay? Not just at the data level, but at the metadata level. So all of these operations are handled using these transaction logs. I'll come to that next. So, and the best part is what Delta guys have done is they're not just processing the data using Spark, they're also processing the metadata using Spark. So all these transaction logs that I'm talking about, they create some checkpoints and do certain optimizations on top of the metadata as well using Spark. Okay, so let's move on. So I'll quickly jump on to the central idea here. The central idea here is that of a delta log. Okay, when I say the delta log is something that we'll be focusing on. One thing I want to focus on in this session is basically delta log, and that is basically connected to all the features that they're providing. Okay, the features, as I've noted down here, is asset guarantees, time travel, CDC, concurrency, single source of truth. Everything is tied to the delta log. Okay, so we'll see how it is tied to the delta log. So the first point here is single source of truth. Okay, so I'll just try to give a general intuition about it. So so this is one set of problem that we face currently. If you've run a Spark job, you know this has happened with you definitely, that your job has half run, right? And you're left with some corrupt files. You're left with some files which are not supposed to be there. Okay, so let's look at this example. So you had your delta table which had 1.parquet and 2.parquet. These parquet files are present in your current data. At T1, job 1 was started. Okay, and it is just a, looks like it's just a simple append operation. File 3 and 4 is there. It is supposed to create 3.parquet and 4.parquet, right? So that is run. The job fails somehow. It failed while writing 4.parquet. 4.parquet didn't get written. 3.parquet got written. So now you have 1, 2, and 3.parquet, right, in your GCS. At T2, job 1 ka version 2 started. Same job, same files it is trying to write. So it creates 3-.parquet and 4.parquet, right? These, now if you see here, nobody knows that nobody knows which file is the correct file, because there was already a corrupt file 3.parquet. When you will be reading through Spark, the extra file, because the system is not aware, the extra file will be read, and there would be and because it has been written, it's a legit parquet file, there would be some problem of double counting. There would be some problem of redundant data in your system, right? Corrupt data in your system. We might even call that. So this is the problem which you had with your normal Spark jobs, right? And then what did Delta do as a solution? So if you see here, Delta introduced this concept of transaction log, the Delta log. It's also called transaction log. What they did was, after writing your 1.parquet and 2.parquet, right? So still now job 1 starts at T1, tries to write 3.parquet and 4.parquet, but it fails. So even if it has written 3.parquet, it's not recorded in the transaction log. So say suppose your starts with transaction log, the leftmost 1.parquet, 2.parquet. When job 1 failed, the 3.parquet is not added in the transaction log. So the first intuition that we should get is it has nothing to do with the job. The job is still a plain old Spark job, but the Delta has everything to do with these transaction logs. Okay, and finally, when your job 1 V2 ran, it added 3.parquet and 4.parquet, right? And if you see, that is recorded in the transaction log, 1.parquet, 2.parquet, with that 3.parquet and 4.parquet, right? All the 4 are recorded. Okay, so you can already see an intuition. So say suppose you were a Spark job next who was trying to read this location, this Delta table or this GCS path, right? What would you do? You would go to this transaction log, and you would not try to go to the path and try to read all the files from there. If you would do that, you would read all the files, including the 3-.parquet. But you would rather read the transaction log first, get the name of the parquet files from there, and then read it from the GCS path, right? So I put this problem so that the intuition is there. And if you see, this is what has been mentioned in multiple blogs and everywhere on Delta Lake. If it's not recorded in the transaction log, it never happened. Okay, it never happened. And this is the guarantee of atomicity, right? Either it happens fully or it never happens at all. Okay, so if it is recorded in the transaction log, it has happened. If it is not recorded, it has not happened. Okay, although you can see there is a problem that once you have written corrupt files, right, 3.parquet is still there. Delta is not solving the problem of deleting 3.parquet. It is solving the problem of recording it. There are ways to delete it. That is a separate part, how the housekeeping, the vacuum, and all those things are done. But Delta as a engine is trying to solve this problem of recording each and every information so that it gives you a transaction processing capability on top of it. Okay, this is the main intuition behind it. Okay, so this is how it kind of gives you, it gives you the guarantee of atomicity. Okay, so next, okay, so let's look at the directory structure. Okay, how it looks like. So if you see here, there is your main table, and then there is a Delta log within which there is this 00.json, 001.json, And then there is your date. This is a partition, right? This date is a partition based on which you have partitioned your directories, and then you have your data files. For example, I'll show in one of our actual delta tables. Okay, this is one of our how it looks in GCS. Okay, so this is one of our GCS bucket where you can see this IDU vertex delta table. This is a bucket. In this bucket, you have this delta log. Okay, within the delta log folder, you have this 00.json, 001, 002.json, right? And when you go back, you have actual partitions. Our partitions are based on ID type, right? IDM ID 1, IDM ID 10. Within this IDM ID 1, you might have other partitions, which we do have. And no, we don't have. So within this, you have the Parquet files. This is where your data actually resides. Okay, so what's the difference? If you see with it, when you write with a Spark job, there's no difference as such, apart from this delta log folder. Okay, there's a change data, I'll come to that later. But apart from this delta log folder, there's no other difference. This is your plain old Parquet files, right? But you have this delta log folder now. Okay. All right. So I'll go back. This is how your directory structure looks like for delta. So you have a delta log within which all these .json files are there, which corresponds to your transaction. I'll explain that next. Okay, so let's see how it looks like. As I've already said, delta lake format is your normal Parquet plus delta log. This is how it looks, right? Your delta log, which I just showed right now. Okay, now let's talk about these .json files, 0000.json. Okay, these are very important in the context of delta table. Okay, so the synonyms you will find as transaction log, .json file, delta lake transaction log, delta log. These are all synonyms. Okay, what do they have inside there? Okay, so first thing is each JSON file corresponds to a version. Okay, which corresponds to one JSON file, which corresponds to maybe your one separate job. Each job that you're running, when I say job, it may be a Spark job, which is trying to ingest your batch data into delta table, or it is a Spark streaming job, which is trying to ingest your micro batch data into the delta table. It can be anything. It can be a batch job. It can be a streaming job. But if a set of records has been committed to your delta table, you will find it as a new version. Okay, so you will find it as, so if the first version is 00, obviously, after that you will have it like 001, 002, like, okay, and then you have this .json file. So and within this JSON files, you will have exactly what files have been committed. Okay, we'll come to that, but it's basically ordered record of every change that has been performed in your system. Okay, what got added, what got deleted, what got updated, all these records are maintained within these JSON files. Okay, and I've already explained single source of truth with an example. Also enables optimistic concurrency control. We'll look into that. Okay, so just remember this: every JSON file corresponds to a version. Each JSON file within it has ordered atomic commits. Okay, the commits that you have made, they're ordered and they're stored here. Okay, so what kind of atomic commits is the next question. What is stored, right? So these are the kind of information that you can find when you open one of these JSON files. Okay, there's an update metadata. Okay, if you're updating tables metadata, so if you want to enable change data, CDC, change data capture, or you want to alter the table, right? So those kind of metadata, when you change for a table, that will be recorded. Okay, then if you're adding a data file to the transaction log, so when we say adding a data file, it means you're doing some append operation. A simple append operation will add a data file. Okay, and that corresponds under the add file. Okay, then there is a remove file operation. Maybe you're deleting some data, right? That corresponds to all the records correspond to that delete are part of some data file. Okay, okay, so then remove that data file. But remove doesn't work so simply. I'll come to that again. We'll look into the internals of that. But right now, as a high level operation, you can think of it like add, remove, set a transaction. Okay, that this is especially for structured streaming job. If you're changing some protocol, Delta also provides you with the facility that, you know, if you are moving on to a newer version of Delta, so that is also recorded. Okay, and finally, commit info. Commit info is basically information around the commit, right? What operation was made, from where, at what time it was made, those kind of information. Okay, so these are the operations that will generally be recorded. Okay, so what happens really when a read job happens? Okay, why, when we have recorded so much information, right? Within these JSON files, we have recorded so much information. Why are we doing it, or what really happens when a normal read happens? So if you see here, with a normal Spark job, what happens is your Spark job, when you provide a path to your spark.read.say parquet, and you provide a path, it just goes and calls a list from operation on your blob storage, right? You'll have some utils, and that's generally very slow. It's the bottleneck, right? It will take a lot of time. If you have if you have petabyte scale, it will take a lot of time. Okay, and what Delta Lake does in this optimization is it first looks at the Delta log folder. Okay, and if you see, there is a concept of recreating state as well through this. It starts reading from 0000 JSON. Okay, so there you might have added some data, and then you have deleted the same data in 001 JSON, right? So it will read 00 JSON. It will try to get all those files. Then it will read 001 JSON, and it will figure out, okay, these files need to be deleted, and this is the final state, right? So there's a concept of reconstructing state, right? By reading these files, by reading the transaction log first. Once you have read the transaction logs, now you know which actual Parquet files to read. So it will finally go read the actual Parquet files from the path. Okay, so this is a high-level optimization because you don't need to now rely on your blob storage, right? And then it unlocks a world of other operations, which we'll see on top of your metadata, which is actually enabling us to do all sorts of transaction processing and stuff. Okay, so I've written a small intuition here. So if you see the 00 JSON, obviously they must store then the path of the data, right? What do they store? They definitely store the path of the data, the path of the files, the kind of operations that have been performed, some sort of timestamp, right? So you can think of it that way. So let's look at one JSON specifically. Okay, this is a very special JSON in terms of Delta Lake. 00 JSON, you'll always find it at the hem. If you see, if you look at the structure here on the right side, I've just tried to do a print schema here. It has some columns, which is add, high-level columns, add, commit info, metadata, protocol. Okay, so the add column will house, if you see under this here, okay, I don't know if sorry, is my cursor visible? I'm not sure.
Yes.
Okay, great. So if you see here, there's already a path in the schema, right? You can directly query this. You can say, here I have written add, right? You can select add.path, and you can see all the path that can be queried over here. Okay, so the adds, the commit info, the metadata, everything is stored here. Okay, and as we have said, first it will look at the 00 JSON, try to read that, try to see what files are available, and try to read those files. Okay, then there is a very interesting thing here, the operation metric. Okay, we'll look at operation metric, but if you see the schema here, it's saying number of files that were written, the number of bytes, the output bytes, and the number of rows. Okay, how many rows were actually committed, and between how many files, right? So when you write, there are many Parquet files. Between these Parquet files, how many rows were it, and how many files are there? So you can do your high-level, some sort of counting, some sort of reporting also based on this info that is already there. Okay, so I'll move to 001 JSON. So there's a difference between these two JSONs. Okay, left side is the 0th JSON, or the version 0, as I said, we can call it version 0. And the right side is the all other versions. Okay, so if you see, the first version can never have a remove operation, right? You cannot delete from the first version, because whatever data you have, you're writing it for the very first time, correct? So you cannot have a delete. So there is no remove column in the version 0, but there is a high level. If you see here, there is a remove column. So the intuition is, in the first file, maybe you have added some Parquet files, right? 1.parquet, 2.parquet, like I was talking about. And in the second, say iteration on the second job that you ran, you're deleting one of these files and adding one more file. So automatically the remove will come under this side and the add will come over here. When you're adding a file, that file path or that file name with the path will come over here. And the file that is getting removed will come over here. Okay. And then there is all sorts of, I'll especially focus on operation metric here under the commit info. All sorts of file level statistics are recorded. Yeah, I'll focus on that. But just take a moment, look at the difference between the two. Okay. There is also a part called CDC, which I'll be covering separately. But this is the part which handles the change data capture. Okay. And I'll be covering that separately. So I'll not cover it here, but I'll be covering it at the end. So both of them are very similar. If you see add commit info metadata protocol, so add commit info, right? But the remove is extra because from the second version onwards, you can use to start removing and updating your data. And then there is this CDC, which has been enabled. The first file cannot, the first version never has a CDC because that's the root, that's the seed, that's the base, right? So moving on. So now I'm trying to focus basically, if you see, on what was there in 00 JSON. If you look at 00 JSON, I'm just trying to draw focus on operation metric here. Here operation metric and either operation metric. Under this, you have just the number of files, output bytes, output rows. So I've tried to put it here, the number of files that were written. So if you see what this means is this many rows, I think 42 billion rows, what was written within 33,000 files. That is what it means. Okay, and this many bytes were written. Okay, so this can actually be used for your Spark. It can actually be used by your Spark jobs, right? For dynamic partition pruning, or when you enable dynamic allocation, right? All this information is actually used by Spark. Okay, so this is what the 00 JSON houses. But there is a huge twist in terms of what a 001 or further version houses. If you see, there are so many operation metrics that is available on this side. Okay, we just look at them briefly. If you see here, you have source rows. So this is the number of rows that is there in the source, means your change data or your source data frame that is coming. Okay, and this is the target rows. Here target means, the target table means the delta table on which you're trying to write your change data. Okay, and the source means the change data frame or the change data. Okay, so how many rows came in your change data? Okay, how many rows were inserted? So all we wanted to do all these years was keep a track of when I am merging my change data with my snapshot, keep a track of how many rows got inserted, deleted, updated at a high level, right? This here it is providing that information at each in the transaction log, basically. How many rows were inserted, how many rows were updated, how many rows were deleted. I'll come to this, how many rows were copied, when I explain the copy architecture. But point is, all this information at a high level is written, is logged for you. Okay? How many total output rows were there? How many total output rows were written? Okay, so you can get a high level idea of how much of the changes or how much of change data capture is going on in your system. Okay, and then at the end, if you see your execution time millisecond, scan time millisecond, rewrite time millisecond is also being noted. Okay, the entire operation, how much time it took. So earlier, if you see, it was tough to measure. Why I took this here is because I've taken an example here as well. Earlier, when you ran a Spark job, which would be very neck to neck, it was tough to measure the metric, how much time it took, right? Given the same resources, how much time it took. That was very tough to measure. But here, when you go ahead and you can actually get the measurement from the version file itself. Okay, how much time it took to scan all the rows, how much time it took to rewrite, how much time the entire job took. Okay, so if you're looking for very small improvements, right, it is very tough to measure on your own. But here, all these information are being logged for you. Okay, so I've taken just an example that the number of rows that were added, or the number of files that were added, the number of files that were removed. Okay, I just took from one of our data sets, one of our JSONs, and put it here as an example. All right. So finally, if you see, now there are so many JSON files that are getting written. Okay, I've spoken about so many JSON files getting written. Eventually, sorry, my bad. Okay, eventually, what is going to happen is, let me just take you to this folder, Delta log folder. Okay, all these are version. So what I was saying is, all these are versions. In this version, right, what I have shown is getting written, right? And within that, you have all the scan time, execution time, the rows that were copied, the files that were added, the files that were removed. All this information is available within these JSON files. The 00 being the special JSON has only add, 1, 2, 3, 4. All of this has add, remove, metadata, CDC, everything. Okay. But the problem, if you see here, eventually, already if you see, we have come till 55, right? Eventually, what will happen is this will outgrow, and the advantage that they had of listing, they wanted to get rid of the listing operation, play around with this metadata, would actually become cumbersome if we keep maintaining so many versions, right? Because then Spark would be busy most of the time manipulating these .json files, right? And JSON is not a very good format, as we know, right? In terms of processing, okay? So what they came up with is a checkpoint file. Okay, Delta, every 10th version is checkpointed. Okay, so all the information that is there from 0 to 9 is collated and merged into this one solid Parquet file. Okay, so say suppose you are at 12.json, what you can do is you can either read from 0 to 12 and reconstruct the state, or you can read from 10th, the 10th checkpoint, which will have all the information from here, and 11 and 12, साथ में 10, 11, 12, and reconstruct the state. That's it. So basically, this is a handy way of keeping your information or keeping your transaction logs from not growing. You know, the small file problem, as they say, of not growing too much. Okay. So eventually, they do it every 10th file. So if you see every 10 version, probably. So you have it here. If you see, right. So the latest state for this system, I can start from 50. And I can reconstruct it but just by playing these versions, 50, 51, 52, 53. Okay, I can go ahead, I can play these versions and I'll be up to date. Okay, so obviously these files get deleted. There is a regular housekeeping that runs. It's not it's not a separate job. It's part of your job, because all you need is these checkpoint files. So these are periodically deleted by Delta itself. Okay, when you run your normal jobs, periodically it will be deleted. There is a threshold that is configured. Beyond that threshold, whatever these .json files are there, they are deleted. Okay, why we need the threshold? Why some are kept? We'll look into that. Okay, so I wanted to show in a practical example how we have used it and give an example there. Okay, so next I just wanted to talk about checkpoint. So checkpoint has, like you can see, if you really think about it, all that is relevant is what to add and what to remove. So checkpoint has that information: add, remove, and metadata. That's it. Okay. Idea is to remove the small file problem, and it again stores in the native Parquet format. So Parquet format, as we know, is a columnar format, which is very fast, and all of this is taken and stored in Spark. If you go to the storage tab on the Spark tag, you'll find that all of this is cached, is locally checkpointed or cached into Spark when you read a Delta table. So this is very fast. This is in memory. All these transaction logs are in memory for Spark. Okay, the data, as you process it, when you call an action, it gets processed, right? But these transaction logs are already there into your cache. Okay, so like I said, always look at last checkpoint plus the transaction log after that point. Okay, so this is more or less about the checkpoint file. Okay, this is way of handling it. Next, we'll move to optimistic concurrency control. Okay, how Spark enables that and what are the problem it solves. Okay, 1 second. People are still there. All right. So the idea behind this is actually taken from, again, RDBMS. The idea here is the likelihood that users working on different parts of the data is high. If you have partitioned your data properly, right? What is the likelihood that you'll be working on the same record, right? And this is the idea here, okay? The idea of mutual exclusion, if you see, right? Mostly people will be working on different parts of the data, right? And when two or more commits, they conflict, right? When two users, basically how it will conflict is maybe two users are reading the same version, right? And one of them wins to write a new version, okay? The others will have to synchronize. That's the idea basically. And that is how it ensures isolation, right? Whoever is the first to commit, the others will have to synchronize with it, okay? So if you see, this is a way to make the jobs concurrent, right? So when you look at these JSON, okay, I'll just go back. When you look at these JSON, doesn't it appear that they are serial? They have been written in a synchronous manner, like every time one job ran after the other, right? But they have been processed concurrently. Okay, they have been processed concurrently, and they have been written by different jobs which were working at the same time, right? But that is the guarantee that Delta Lake provides. Okay, that the logs, when you see, they will be ordered serially. Okay, you'll always see a serial view. You always see a monotonically increasing view, right? And that's what ensures the isolation part of it. If two of them have read the same version, two jobs have read the same version and made changes, whoever wins to write the next version, the others will have to synchronize. Okay, we'll see an example here. If you see here, so user one, and in this example, user one and user two, they read 0.json. This is the version corresponding to 0th version, right? And that might have 1.parquet and 2.parquet, right? And both of them are attempting to append data. Okay, so both of them, when they write, they're trying to write 1.json. Okay, but user one succeeds. As soon as user one succeeds, Delta doesn't throw an exception. Okay, Delta handles it optimistically. Okay, it checks if any new commits were made. Okay, yes, new commit is made, 001 JSON is available. It reads it. It sees, okay, this is the case of no conflict actually. It sees whether it is conflicting with any of the files that it is working with, user two is working with. Okay, if not, then it will just go ahead, try the user two ka commit, which was earlier going to be 1.json, try that same commit with 2.json. Okay, now there might be a conflict also. Okay, so basically user two in its 1.json version, or in its version 1, okay, it deleted some file which user 2 needed, right? Deleted some file. So in this case, there will be a concurrent modification exception. Okay, but it will not corrupt the table. At any point in time, it will not corrupt the table. All your changes will be stored on your blob storage along with the particular commit logs. Okay, and that is how it ensures durability. Right? All your changes goes through in an atomic fashion, and whatever could not be written, it synchronizes, reads back the next version, right? And writes either as 2.json or throws an exception. Okay? But it will never corrupt the table. So you can be rest assured, you can run this job. If they're working on two different parts of the data, two different partitions of the data, two different sets of rows, say, you can be rest assured that the first job will write the 1.json and the second job will write the 2.json. If they're working on the same row, right, then there will be an exception. Only if they're working on the same row. Okay. So this is about the durability part of it. I'll move to something which is MVCC, multi-version concurrency control. So here you're just looking at the normal optimistic concurrency control. But how does so basically what it means is concurrency control across multi-version, across multiple versions, right? How does that work? Okay. So this is basically, again, this enables time travel. This provides some transactional guarantees and query uh, and query performance, mainly query performance or write performance. Okay, it is based on this premise itself, the likelihood that you're working on different parts of data, but it has an additional tweak to it. Okay, the additional tweak is copying data. I'll explain how it works. So first, like here, you read the data, right? And you do an optimistic write. What does an optimistic write means? So you're supposed to make some additions to your data. You're supposed to add some rows, okay? So you stage all your changes by writing new data files. So when I say writing new data files, every change, an insert, an update, and delete, everything is writing new files. A delete will never go, and there is no delete of older files. There is no concept of delete over here. Every data file that is available in your Delta Lake corresponds to a version and is logged inside the transaction log, inside the JSON files. Okay. If a new delete happens, if an update happens, that also happens in the form of writing new files. So this is very important because all changes that you make, you write new files for them. Okay. And then you do this, what I showed here, basically validate and commit. First you validate, within this time, has somebody else written a version or not? Okay, they haven't written, then I will write. If they have written a version, then you synchronize that. Okay, let me read. Whatever they have written, are they conflicting with my changes or not? Okay, they're conflicting. You throw an exception. All right. Okay, they're not conflicting. Then I will go ahead and write my new JSON file. Okay, 2.json or new version, as we can call it. The central idea here is everything will be a new data file. So I'll elaborate with an example. So as you can see here, because everything is a new data file, there are multiple copies of your data that are stored. Okay? Hence the consistency part of it, right? A reader continues to see a consistent view of your table. At the time it is getting modified. Why? Because the reader is reading an old version. The reader read 0th version. So the reader is at 0th version. No files got deleted while the reader was accessing it and working with it, right? Reader is at 0th version. No files got deleted. New files got created as part of delete. Okay. So the reader who is on 0th version sees a consistent view, right? The reader who is at the second version will actually see the deletes happen, right? But that is also in the form of new files. Okay. So what do I say when I say new files? Okay. Look at this scenario. Okay. If you see here on the right hand side, we have this one.parquet, which houses, I'm just talking about some ID over here. Okay. Generally, you'll have a primary key, right? 3, 4, 5, 6, 7, 8. All right. So these are the primary keys, or these are the ID that is available. So when you want to append data, what you'll do is you'll append 9, 10, 11, 12. So that will become part of, so this is part of one.parquet, that will become part of 2.parquet, right? So if you see here in the metadata, what will be stored? A new version. So say this new version, I just want to add files. So a new version will be recorded. Along with that, add this 2.parquet's file in the add column will be recorded. As simple as that. Okay. Now you want to remove this 4th ID over here. Okay. What is going to happen is a new file will be written, which will have 3, 5, 6, 7, 8. Okay. And this file 2.parquet, which they're saying, this will be marked for add. And 1.parquet will be marked for remove. But in this version, it's a new version. In the old version, 1.parquet still exists. In the new version, there is a 2.parquet, which is marked for add, and there is a 1.parquet, which is marked for remove. And this is how you do multi-version concurrency control. Every version, no matter who it is, writes a new file, even if it's a delete, even if it's an update. So corresponding to this 4, you have male, gender as male, right? You want to update that to female. Okay. That is also updated in a new file. And that file is marked for add, and this file is marked for remove. Okay, so the old file, that's how we call it, tombstone, right? In Cassandra also it's there. The remove part is of those metadata of those logs is called a tombstone. It's marked as a tombstone. Same for update, same for even that is the same how compaction also works. You want to compact 4 files into one file, right? So what it does is it will take all those 4 files, take all their data, put it in one file, mark that as add, mark the rest as remove. So the idea here that I was trying to explain is everything is an optimistic write. You stage all the changes first, write new data files, right? Whether it's insert, update, delete, everything, right? And then you validate, okay, somebody else has written or not. If not, that new version is written. So across version, you have this, capability to time travel, right? I hope. Second. Yeah. So that's how the consistency piece is maintained, okay? By keeping multiple copies of the data at any point in time, a reader reading a previous version, okay, that the files won't get deleted, the files won't get suddenly updated, because all these updation, all this deletion, all this insertion is happening to a newer version. But what that means is the cost, the trade-off is keeping multiple copies of the data, right? So that's how that works. Okay, so next, if you see, I have just put down some operations here, how the different operations that we are really concerned about works. So if you see here, 1 second. Okay, sorry. So if you see here, the update operation is something that I have put here. Although we don't use it, but it is a good use case to explore. So the simple operation is you're updating some events table, and you want to set the event type to click, where button press equal to 1. Okay, so everywhere where button press matches 1, you update this click event. Okay, so the operation how it flies is find and select the files that match this predicate, right? Read only those files into memory. Okay, update the relevant rows, write results into a new data file, mark the old files for delete. Simple. That's how an update works. Creating new files, marking the old files for delete. Simple update based on a predicate. Okay. Now, if you can see, all your optimizations will be around all these finding predicates, right? Because the more efficiently you can partition your data, the more efficiently you can structure your data, the easier it will be to find these files. The less data it will have to scan. Delta or Spark has to scan lesser data, right? So it's kind of a hint also to where to look for optimization when you're using the update operation, okay? Because anyways, you can't stop it from creating multiple records, because that's how it maintains concurrency. Okay, guys, just stop me if there is any confusion or any question in between. Next, this is the most important operation you'll probably want, because it provides you with a merge operation, upsert operation. So I've just taken a dump from my IntelliJ, because it was kind of on the right side, this showing the output type, the return type, basically. So I thought this would be easy. So they have this delta table, which is a class, and you can load your delta table using for path. Okay, that returns a delta table to you. We have named it as snapshot, and we're trying to merge something called CDC. Okay, if you see, it's quite readable. If we're trying to merge something called CDC, which is our change data capture, it's just a variable. It's basically a Spark data frame. We've aliased it as updates. There is a join condition, if you see here, so which kind of gives us an intuition that there must be a join involved somewhere, right? We're trying to join on something, right? There are two ID and ID type we're trying to join on. You're saying when matched, update everything. When not matched, insert everything. So basically, your updates has all your data that either needs to be inserted or needs to be updated on the snapshot, right? That's what we want when we want to grow a table. Either it's an insert or it's an update, right? So that's what is happening here. Okay, and to show how it works internally. Okay, so the insert operation, if you see here, as I said right now, when update is when matched, insert is when not matched, right? And if when you go, you'll um, you'll never find an insert operation on matched. When you do a control tab on your IntelliJ, you'll not find one. Okay, because that's how it should be, right? When there is no match, you insert those records. When there is a match, you update those records. Okay, and then here I have given update all. You can update specific columns also. You can leave out certain columns and update specific columns. Okay. To give an overview of how this operation works, there are two joins that are involved over here. Okay. The first scan is an inner join. Okay. The inner join finds a match between your target and your source. Right. What's your target? Your target is snapshot. That's where you want to update things. What's your source? Updates, this data frame. From where you're taking the updates. This is your source from where you are taking the updates and updating your target, right? So first, it does an inner join to find the matches. That's how it can say what matched and what did not match, right? And the second one is an outer join, where it takes the selected files on your target and your source, right? It pads it with your insert, updated, delete data, right? So one side there will be a match. So then it will match all your inserted, all your updated data. When there will be a no match, then it will pad all your inserted data, right? And then it will go ahead and update. So there are two joins that are involved here, right? And that's how the merge operation works. But if you see, all of this is handled at a DSL level. Internally, these are Spark joins that are happening. They are also optimized by Spark. You can give hints for broadcast, things like that. But the point is, all of this is handled by this DSL. And you can just focus on the business logic of how you want to perform transactions and not worry about anything else. Okay. So basically, just summarizing here, we've looked at our transaction logs, how it enables multiple copies of the data, how it enables delete even by copying the old data, removing the deleted data, right, marking it for tombstone. How you can go through versions. You can go to a previous version. A reader who is reading the data can go through a previous version and still query that version. So they are working on that while a newer version is getting updated, right? All of this, is kind of leading us to time travel, right? There must be a way, since you have captured so much change data, there must be a way to do time travel, and that's the next topic. Okay, I have written here time travel as of. That's the operation basically that you will be referencing again and again. When you want to do time travel, remember this term as of. So when you do as of, it will be based on a timestamp or a version, right? Give me the data as of this version. Give me the data as of this timestamp. So the querying is based on that. And use cases, probably I listed a few. You might innovate and find your own. So one of them is here. Maybe you want to travel back to a version, right? So you say Spark read, again, format is Delta. You load it from a path. All your data is housed in the same path. There is no folder segregation, nothing. Once you say version as of, you give a certain version, it will load those particular files. And all of this at the back, if you see, it's powered by the transaction logs, because the transaction logs store this data. Okay, which version corresponds to which files in your GCS. Okay. Second use case may be finding change data. This is a very important use case for us, at least, because we wanted to know what change occurred between two versions, right? For profile store, our main use case for going through so much trouble and migrating so many pipelines was that profile store used to do a join of all the DP merges, which are full snapshots. We wanted to move it to a delta architecture where we are only able to merge delta data from DP merge to the profile store. That would actually reduce. That's what I was alluding to earlier, that you would not have to do high joins, because once your entire system supports delta, you can just flow those delta into your final downstream pipelines, and that is what we are doing right now. We are just passing on the delta data to our MPM. Okay, and this query is very important there. If you see, we do a start version and we do an end version, and between those versions, what change came? That's something that we wanted to look at. Okay, and it returns a data frame to you. Okay. Another use case I've just stated here is based on timestamp. If you want to go back in time, right, you want to find the count of data at a particular time. What was the count of data? So you can just go back and load it based on timestamp. Okay. So after this, I just want to show this folder again. I said I would talk about the change data folder, right? So let's talk about the change data folder. So here is the change data folder. If you see here, okay, same partitioning scheme as the main folder. All the change data is recorded here. Okay, so what does that mean? All the change data is recorded here. Okay, so the change data. So over time, what we do is when the delta log is being created, right? If you see here, when these delta logs are being created, there is a checkpoint every 10th version. The checkpoint has nothing to do with the change data. Okay, these transaction JSONs or these version JSONs are the ones who are storing the path to change data. Okay, so what does that mean? Let me show an example here. Just 1 second. Okay. So if you remember from a previous slide, actually I have it on a previous slide. Let me just go back there. Yeah. If you see here, you had your add part and your remove part in this schema. This had stored what files were added, what files were removed. This serviced the state rebuilding, the reconstruction of the state. When you're looking at a certain version, what does this version entail? Oh, I have to pick these files, I have to remove these files. This is my final version. Okay, but this data is not stored in the checkpoint. When I was talking about the checkpoint file, if you see the checkpoint file, it has only add and remove. There is no concept of CDC over here. But if you see here, there is a CDC column as well available. This CDC column, if we go and if we check, okay. Okay. Sorry. Okay, my bad. I think the screen was not visible. So this CDC data, this column, okay, I'll just do one thing. I'll just quickly share my screen and show a demo quickly. It'll be easier demo. One second, guys. Okay, so if you see here, I have loaded the 0001 JSON, okay, and I have loaded the 0 JSON, no worries. I'll do is, if you see, the print schema over here, all right? So you have this column CDC. This is where all your change data is being stored, okay, and that is part of each transaction JSON. It's not part of your checkpoint. Okay, so we'll see what it stores quickly. So right. See here, under the CDC column, okay, we have a path to the change data, which I was talking about, right? So the schema is available here. Data change, first is data change. It says false, partition values, path. This is the path, change data. So all the change data is written. So there is a double copy here. All the change data, I'll go back to my slide quickly, second. Is screen visible? Okay. All right. Sorry, guys. Okay. So let's go back. So if you see here, all the change data, how Delta is handling is, how can they provide just by writing what files to be added and deleted, you cannot give me a dump of the operations that were performed. You have to store it somewhere, right? And that is what they do. They store actual operations with the data. They copy exact data, all the data that you have. They store exact operations with the data in this change data folder. Okay, I'll show a demo at the end, but just stay with me. So if you see here, within the change data folder, this is your change data folder. I'll go back, just to refer back. This is your change data folder. If you see exactly same structure, right? Exactly same structure. I'll go into one of these folders. Parquet files are here. Okay. What does this Parquet file look like? The schema is this. This is the exact same schema of your data, the data which you just inserted, deleted, or updated, with just one addition. The addition is this, which I have highlighted, change type. This change type denotes whether it's an insert, whether it's a delete, and there are two other operations called pre-image and post-image. Okay, what is it? I'll come to it. So one thing, this is not recorded in checkpoint file. Just having a checkpoint file would not tell you how to travel back in time. The .json, the transaction log, the delta log is required to travel back in time. If that is deleted, we faced it very recently. If that is deleted, your change is somewhat lost. We found a workaround as well. I'll talk about that. So, okay. So let's look into this transaction log now. Okay. We went to the change data folder. Okay. The change data folder is now maintaining history. That means it's copying all your data, right? It's double writing, it's copying all your data. What do I mean by double writing? So there are four operations really. Okay, I've taken just a distinct or just a simple operation dump. If you see here, this is called update pre-image, update post-image, insert and delete. Insert and delete is simple. A new, oh, it's not getting shared. Kya? Oh, sorry. You सुन नहीं रहा है क्या? तो अपने काम में busy. Hello.
Hey, yeah.
Okay. Just mic testing. Okay. So what this change type has, if you see, there's an insert, whatever operation, say suppose a new row has come. It is part of my version file, but it also gets written in the change data, duplicated in the change data as an insert. Oh, this row got inserted. This row got deleted. Okay. And if a row got updated, the entire row is taken, the previous, before getting updated, that entire row is taken, recorded as a update pre-image. And then the updation happens and that row is taken and recorded as a post image. These are the four operations that you will find in the change data. Four operations. Okay. So that means there's a problem here. There's a trade-off here that all this data is getting replicated in your change data. So when you use it, when you're using CDC, very great, you're using time travel, but there's a cost that you're paying in terms of storage. Okay. A lot of data getting written, but then storage in terms of GCS or your blob storage is cheaper nowadays. So, that's the concept behind it, that we can keep extra storage, but not lose the state or enable transaction processing using it. Okay. So again, this is tracked through your transaction log, like I showed here, right? Transaction log has that column CDC, which has the path. Using that column, that path, it will know what file to pick from the change data folder. So if transaction log is lost, everything is lost. Okay. And I'll very quickly show a demo here. Give me just 1 second. So that, it will just settle down what I'm trying to say. Second. Is my screen visible? Okay. So look at this, what I have done. It's a very simple thing that I have written. What I've done is I've taken some records here. Okay, this is the record. You see here, the record is very simple. This is the ID column, ID 1. I have male 25, ID 2, male 25, ID 3, male 35. And on this, what I'm trying to show here is change data capture. How does the change gets played on your data? Okay, so you have the first change as row, as on the first element, it changes it to age, the age is getting changed. Okay, so like this, I have a series of changes, right? That is getting played. Okay, your table में 3 ही रो रहेंगे, यहाँ पे एक 4th ID gets added. So at the end, you should have four IDs. Okay, so let me quickly play this and show what I mean. Okay. So just allow me some time to just quickly show this. That this will actually concretize what I have been talking for such a long time. Okay. We have, yeah. Show the logs for entertainment. This is just my local that I'm running, but it's a very simple operation where what I'm trying to do is, this is my starting snapshot of the table, and each of this row, if you see here the code, I'll try to explain the code while it runs. For each update, this is the update list. This is the update ka list. For each update, I'm creating one data frame. So it's a data frame which has one row. And for that one row, I'm trying to merge it with this delta table. This is a delta table which I have written. Analysis exception. Okay, something. I'll check. Oh, my bad. Sorry. One second, please. Delete it. Load it again. Yeah. Now it will run. Okay, so all I'm trying to do is create one row ka data frame. Okay, and update my snapshot. So eventually, what you can see is 1, 2, 3, and I'm not deleting anything. So you can see the 4th ID ka row as well. All right. And that's what this guy is doing. When you merge it with this data frame, which is a 1 row ka data frame, and which will basically, when it is matched, it will do an update. And when the 4th row comes, it will not match and it will do an insert. Okay, and this is the execute is the action that we have to invoke to get this entire ball rolling. Right. So right now it's basically that. But what I'm trying to show here at the end is how the history of the delta table looks, how the delta table at a particular version looks, and how the change data looks, so that you can do time travel, go back in time and see what can be done on change data. So it's almost done. Just, end anytime now. Chalo, chalo. Okay, is ended. So let's quickly look at the delta table, right? So look here, delta table dot history to evaluate. Let's see. Sorry. Oh, false. Yeah. So you see here, look at this history. I have done all the merges, right? What I was talking about. I've done all the first was a write because it was the first entry point, and then I did all these merges, right? Okay. So all of that, this has been recorded. All the merge that we have done has been recorded into the system. All these merges were action type was insert, right? And 1 second, let me quickly show how the change data also looks like. Okay, let me actually show the data as well. I think 1 second. It's not yet updated. Go back. Just okay. Look at the change data which I was talking about. If you can take a look. So everything, right? Currently, when I loaded everything, it is showing as you know, the 4. So what was the updates that we are trying to do is we updated 1 to, let's go back here, right? First we updated 1 from 25 to 35. So the 1 here should be somewhere together. It is written, see, 1 here, because I've just loaded the Parquet files. I don't know which partition to load, right? So it's not ordered, but 1 here with 25 shows as a pre-image, and then 1 here with 35 shows as a post image, right? And like that for all of them. For 2, if you see, first I did with 100, I updated 2 with 100. So somewhere there will be a pre-image here. Where is it? Here. 2 ka pre-image with 25 and post image with 100. Okay. And that is part of your change data folder. This is what resides, and this is how the operations happen, okay, in your change data. One thing that I did, actually, there is 20 rows coming up. What I should do is I should just pull 21 rows. I think there might be a the insert is missing, actually. I wanted to show. Yeah. See, for 4 is part of these files, right? My condition was if when it is not matched, insert, right? So 4, first time when it encountered 4, it inserted 4. So if you see here, 4 got inserted here. Here, this is the first time 4 was encountered. 4 female 18 was inserted. So this is what resides in your change data. Okay. But at any point in time now, my delta table, the name here is table. Let's see. Delta table dot UDF dot show. Look at the delta table. This is the latest version. It just shows 1, 2, 3, 4, right? Having said that, you have all the versions available with you. You have all the changes that occurred. So you can, go through these changes, write certain queries, go through these changes, and calculate the change data, right? How the changes and everything happen. Okay, so I'll just quickly finish it off. I think just over time a bit. I'll just finish it off. So this is how the change data works. Okay, and restore, when you restore to a previous version, right? When corruption happens in the data, no need to, since you have so many versions, no need to rerun the job going forward. When we rerun Spark jobs, right? Just restore to a previous version. How? You can use one of these. Best is this one. Restore to a previous version. Restore to version. That's it. How does restore work? Again, same funda. Even the best part is restore doesn't even play with data. You had version 0, version 1, version 2. If you see, version 0 में file A add हुआ, remove हुआ, version 1 में B add हुआ, version 2 में remove हुआ B, C add हुआ. Version 3 goes back to version 1. Okay, all that was left to be done was, right, add file B, remove file C. That's it. It's a metadata level operation, and your restore is done. Okay. Okay, so to summarize, what we got is obviously serializable ACID writes, snapshot isolation for reads, right? Each read can work on different versions. Scalability to billions of partitions or files. You run your jobs on different partitions. Self-describing metadata, like I showed here, I just loaded the metadata, queried the metadata, what got added, what got removed, what got pushed to change data. Every log is there in a very efficient manner, and support for incremental processing, like CDC, SCD, all of that. Okay. Next question is, when should I use Spark or Delta? Simple. From now on, having this knowledge, if you have a table-like structure, never use Spark. If you have exploratory analysis, if you do not need the lineage, it's a one-off processing of large unstructured data, use Spark. But if you need ACID, if you need concurrency, right? If you need a table-like structure where you need to go back to time, where you need to maintain, even if you don't need that, use Delta, you'll find a use for it. Okay, because maintaining just a small metadata doesn't hurt, but you never know how your data will evolve. Only when you're absolutely sure this is a one-time work, that I process my data, it's one-time work, then use Spark. Otherwise, use Delta. It costs nothing, but gives back a lot. All you have to do is write it in a Delta format. Okay, how to convert it to from Delta to Parquet? Delete the Delta log folder. It's back to Parquet, at least for one version. Subsequent versions, you have to use some quirks, which we can discuss alag se. Okay, so caveats, while working with Delta, we figured out some caveats. Okay, so I just thought I'll mention it here. For the sake of time, I'll not elaborate much on this, but idea is there's no duplicate in Delta Lake. If you have duplicates in your target table, okay, or in your source table, there can be, indeterminate results. So ensure that on both sides of the data, there is no duplicates. Okay, because primary key, there are no duplicates in primary key, right? If you have duplicates in your primary key, then same columns and same data will get replicated. Okay, so that is one. There's one issue with Yatharth has raised. It's a good issue. You guys can go and check it out. It's there on this slide. So your CDC does not detect if there is a change in the row data. Okay, I'll leave it to that. It's an interesting issue. Delta has said they'll not fix it. There is a workaround for it, application level workaround. You might want to check it. Okay, but the idea is when you have a CDC, Delta will not look at whether your snapshot mein jo row hai and the row that comes from your source, whether they are same or not. It will update it nevertheless. And sometimes when you have such kind of data, which has a lot of similar columns, both in source and target, you might want to filter them out, because otherwise they're just going to keep updating the same data and keep blocking your CDC. Okay. Next is map key updation. Map as a data structure is not very well supported. You cannot go, if you have a data structure, if you have a column, which is a map column, you cannot go and update the key for it. You have to replace the entire map. I actually have a blog on it. I'll share that later. I haven't put the link here. Okay. But the idea is map cannot be updated. Map keys cannot be updated. with a value, basically. Third, very important that we found when we were working with it, delta log gets deleted periodically, right? So CDC, if you haven't consumed it, there's a CDC. How you can go to the CDC, go to the delta log, find out which files in change data, go to change data, consume the CDC. But by the time you came to consume the CDC, your jobs, the delta log might be deleted. So Deepak has written a small solution here, attach the link here. Okay, you might want to go and check it because there's a workaround. Okay, which we do not guarantee will always work because it has some caveats like vacuum should not have been run, restore should not have been done. But considering those were not done, you can actually safely use this change data feed retriever. Okay, and again, be careful with vacuum. If you want to retain the version JSON delta log for a long time, consider increasing this log retention duration for 30 days, or consider backing up your logs even, taking a backup in some other S3 storage or GCS somewhere. And another very important issue that we figured, this issue was actually fixed. We reported and it was fixed by Delta. It's repartition before write. So Delta automatically used to repartition, which had a repercussion on the performance of the job that you're running, the Spark job. So we actually reported it, and it was just a config level change, but their documentation was wrong. So we had some of our jobs failing. So we reported, and they had fixed it. Okay, so these are some of the caveats. I have some of the learnings. I don't have time today. I'll be covering all these learnings, but for that I have to first do the next steps, which is your housekeeping and optimization, which involves compaction, Z-order, custom TTL. Probably these are the next steps. Look out for the next sessions: Photon optimization, structured streaming, and housekeeping and optimization. So these are probably the next steps that we'll be looking at. Yeah, that's about it, guys. Thank you.
Hey, Joy, amazing session. I have one clarification required. So,
Yes.
suppose these transactional log files, suppose I'm looking at the 005.json file.
Yes.
So it will
Yes.
have the metrics as compared to 004.json file, right?
No, it will not. So basically, what happens is whatever has been recorded in 004, okay? So say suppose in 004, you said add 3 files.
Okay.
In 005, you will only record the file that was changed. So you came up with an update in the 5th version.
Okay.
That update will correspond to some row in the data. That row will correspond to some one Parquet file among all the Parquet files. Correct.
Okay.
So that Parquet file will be copied. The row will be deleted, say suppose, or updated, and a new Parquet file will be created. And the old Parquet file in 005 will be marked for deletion, and the new will be marked for addition. So that's why that's the problem. Another problem with Delta is you cannot start reading the state from 5th. You always have to reconstruct the state from the 0 or the checkpoint. So in the 4, you will have 1, 2, 3, 4 dot Parquet. Okay. That stores all the information. In the 5th version, you changed 4. You removed 4, added 5. So now you need 4 and 5 to reconstruct the entire state, basically. So 1, 2, 3 will come from 4.json, and the 5th got deleted and 6th got added will come from the 5th version. So that's why in between kuch nahi ho sakta. Ya to tum koi checkpoint se chalu karo, या you start from the 0.json and reconstruct the state, like calculate ये file add हुआ, ये file remove हुआ, फिर ये add हुआ, ये remove हुआ, and finally you plus minus करके एक final state मिलेगा ना. That is your delta table till that version जहां तक तुमने पढ़ा है.
Correct. So suppose let's for this sake of discussion keep aside the checkpoint concept.
Yes, let's keep aside.
And the metrics which you were showing, right? The how many rows added, how many rows deleted, updates, the numbers and the bytes increased. So that has been happening since from the base file, which is the 00JSON, or the previous one. That was a bit confusing there.
Acha. Okay. Let's go to one file quickly. Okay. Easier to explain that way. 1 second.
Because why that question arise was, if suppose two users are simultaneously working on, let's say, one version, and they update in mid, so how when the JSON 2 or JSON 3 is been updated after the JSON 2 is done by the user 1, and when user 2 is updating, like at runtime all those things are captured and updated?
So see, when both of them started, they must have started with the same version, correct?
Correct.
Now, whoever, like what I said, whoever was succeeded in writing a newer version. When this guy came, the version has already changed. So he has to reread the versions again.
Okay.
Okay. So he has to go back, reread the version and see this version has not impacted any of the files that he was working with.
Mm-hmm.
If it has not, then only it will be able to write a new version JSON. Otherwise, it will throw an exception. कि there is a concurrent modification exception. कि मैं जब modify कर रहा था इस record को, किसी और ने भी कर दिया.
Okay, so then it essentially means that it basically calculates those number of rows added from the previous version, right?
Yes, yes, absolutely.
Fine. Yeah. Thanks. And another question I had in terms of that merge operation, you mentioned that there would be two joins, the inner join and the outer join. But the work done basically, if there's a already matching condition, then you update. If no matching condition, then you add. This could be achieved by only outer join, right? What was the utility or use case of the inner join?
So that is, see, that is a say क्या कहते हैं, that is a optimization which they have done. Means it's a part of their dialect. So they want to first match it. Okay, whatever got matched. So basically, how they'll be writing it is, look at it this way: you match some data, right? So one तुम्हारे source में भी है, one तुम्हारे target में भी है. You match that data, right? Now there is a set of data that is left over, right? Once you matched, then there is an operation that needs to be performed. Match करने के बाद उनको update किया तुमने, correct? उन operations को update किया, और जो match नहीं हुआ उनको तुमने add कर दिया, insert कर दिया, right? So after matching, there is an operation that needs to be done of updation. Okay,
Correct.
that's why they first do a match, update them, and then do an outer join, so that whatever has been matched gets updated and whatever is not matched gets inserted basically. And whatever जो update और insert नहीं भी होगा, उसका भी तो एक subset होगा ना, जो ना update के लिए match हुआ ना insert के लिए match हुआ. Correct? There is still a subset that needs to be padded with nothing and needs to still go back into the newer version.
Okay.
So that's why. But then they have also come up with something called low shuffle merge, which actually we are exploring right now. So probably next session we'll be able to throw light on that. So there are some optimizations that has been done in Photon based on that.
Okay.
So
And one final question. So if we delete the logs of before checkpoint, and if you want to do a time travel, we cannot do, right?
cannot. Yes, that's what I was trying to explain. Okay, time travel has everything to do with the transaction logs. Transaction log gone, time travel gone.
But does checkpoint does not contain all the previous logs within that 10 logs?
It just contains the add and remove part of it.
Okay.
Add and remove में जो है basically वो checkpoint बोलता है कि मैं तुम्हें अभी वाला state reconstruct करके दूंगा, अभी का state. मैं तुम्हें ये नहीं बता सकता कि अच्छा ये रो insert हुआ, update हुआ, delete हुआ, ये नहीं बता सकता. मैं तुम्हें ये वाले को टाइम ट्रैवल मतलब वर्जन टू वर्जन तुम पीछे पीछे जा सकते हो, रिस्टोर कर सकते हो. लेकिन जब when you exactly want कि क्या ऑपरेशन हुआ, चेंज क्या हुआ, that kind of level of operation only CDC और ये change data can provide. तो उसके लिए वो CDC column.
Got it. Okay. Thank you so much, Joy. This was wonderful.
Thank you so much. Hey guys, any other questions? All right, I'll stop the recording. Just ping me if you have any questions anytime. We will sit.